Hello folks, for this video our focus is going to be all about ions. And if we remember, ions are going to be atoms that are positively or negatively charged. Well, our goal is to focus on some of the most important ions for neurons in the plasma membrane of neurons, which are going to be sodium and potassium. So sodium has the element symbol of Na, potassium has the element symbol of K, and these are both positively charged ions. And so our goal is to understand how these positively charged ions move through passive transport of the plasma membrane and, of course, active transport of the plasma membrane. Our focus first is going to be passive transport. And we're going to figure out how these ions move when it comes to their electrochemical gradient, meaning the fact that they're positive and then being attracted to negative charges, and also how they move in relation to their concentration. So if you have a high concentration of potassium or sodium, it's going to want to move down its concentration gradient to an area of low concentration. So let's get into those details first. All right, folks, let's first get oriented with our picture of the plasma membrane of a neuron. So if we take a little piece of this neuron, we'll see that we have our plasma membrane here, and on the outside of the plasma membrane is going to be the extracellular fluid, and inside of the cell itself is going to be the cytosol. Now, the outside of the cell, which is going to be our extracellular fluid, or outside the membrane, is going to be positively charged, and the inside of the cell is going to be negatively charged. And that's going to make sense, especially if we're talking about electrical gradients as we go along. Okay. Next, what do we see? We see a protein here, and this protein is going to make it easy for potassium and for sodium to go in and out of the cell. Now, what kind of protein? We see a leak channel protein. And this is going to allow that potassium and the sodium, as we go along, to passively move in and out of the cell whenever it needs. So let's focus on our electrical gradient first. Electrical gradient means that we're dealing with membrane potentials. And we already know that the inside of the cell is negative and on the outside of the cell is positive. And so there's a voltage that's created from that opposite charge. And we're going to learn as we go along that the inside of the cell is going to be negative 70 millivolts for the membrane. And we'll get more details again throughout the lecture. But that also means that if you have things that are positively charged, like sodium and potassium, because they are the opposite of what's inside the cell membrane and they're positively charged, opposites are going to attract. So things that are positively charged are going to be attracted to negative, and things that are negative charged is going to be attracted to things that are positive. So because I have my potassium in the extracellular fluids that's also positive, guess what? For its electrical gradient, it's going to passively want to move into the cell towards the inside of the cell, which is negatively charged. And that happens simply because you have an ion that is positive and the inside the cell that's negative, and opposite charges are going to attract. Now, when we're talking about concentration gradient, that's a little bit different. Now you're focused on the amount of potassium on the outside and inside of the cell. So here I see I have 1, 2, 3, 4 potassiums on the outside of the cell, 1, 2, 3, 4, 5, 6 potassiums on the inside of the cell. So because there's a way more potassiums on the inside of the cell, what do we know about concentration gradients? Ions want to move from an area of high concentration to an area of low concentration. And because we're talking about passive transport, then our focus has to be on diffusion. Okay? And so just because there's a lot more potassium on the inside of the cell, they're going to want to move outside the cell when it comes to concentration gradient. So the next question might be, well, how do you know which one is going to move? Because we have one of the electrochemical gradient going down and the concentration gradient going up, which one is going to be the one that kind of supersedes the other? And that's going to determine on which one is stronger. So say, for example, you only have one single potassium on the outside the cell and like 18 potassiums on the inside the cell. That's going to be a stronger concentration gradient because you're increasing the difference in concentration between the inside and outside, right? So you're going to have like more rapid diffusion because the potassium cells, ions on the inside are going to say, get me out, get me out, get me out, get me to an area of lower concentration. Same thing with electrochemical gradient. If you're going to, and you're basically changing your electrochemical gradient in a large amount and your voltage changes a large amount, then that's the way we'll be able to determine which one is stronger. But for our class, you probably won't have those details. It's really going to be specific on the electrical gradient or the concentration gradient to make it easy. And with simple examples that we see, it's going to be harder to basically decide which gradient is stronger, electrical or concentration gradient, because we don't have all of the actual data to make the best decision. But overall, we usually say we call both these gradients the electrochemical gradient, which combines both of them in relation to whatever ion we're thinking of. Let's move forward and see some more proteins that are embedded in the membrane for, say, sodium. So again, we're still talking about sodium and potassium ions. And as you can see, now we have two different leak channel proteins, one for potassium and one for sodium. So again, you're going to have potassium leak channel proteins and sodium. So some folks are like, isn't there just one leak channel they could do both? No, they're very specific. So this one's specifically for potassium, this one is specifically for sodium. Before we even get to anything else, let's look at more detail of this. Let's go ahead and count the number of sodiums on the outside and inside the cell. But let's orient ourselves. We have our plasma membrane here, great. We have the cytosol, which means we're on the inside the cell. We have the extracellular fluid, which means we're on the outside the cell. And then we know that the extracellular fluid on the outside the cell is positive and the inside the cell is negative. Let's go ahead and count the amount of sodiums we have on the outside. 1, 2, 3, 4, 5. Okay, on the inside we have 1, 2. Automatically we have a higher concentration of sodium on the outside the cell. So we see. Let's go ahead and do the opposite for our potassium. We have 1, 2 potassium on the outside of the cell, 1, 2, 3, 4, 5 potassium on the inside of the cell. So the higher concentration of potassium is inside the cell. And this is going to be representative of a neuron at rest. That means it's not communicating, it's not trying to move any messages or receive or transmit any messages at the time. It's simply at rest. And so at rest, when you're focused on sodium, you're going to have a higher concentration of sodium on the outside of the cell and a lower concentration of sodium on the inside of the cell. When it comes to potassium, you're going to have a higher concentration on the inside of the cell and a lower concentration of potassium on the outside of the cell. So it's literally the opposite of sodium itself. And when we're thinking of the electrical gradient, because of course we focus on the electrochemical gradient, when we're thinking of the electrical gradient, both sodium and potassium are positively charged. So they both want to go inside of the cell because the cell is negatively charged. So let's look at the potassium leak channel. For its electrical gradient, it's going to want to go inside the cell. And for sodium, its electrical gradient, it also wants to go inside the cell because they're both positively charged. But let's see what happens when we're thinking of what happens with the concentration gradient. Again, that's where we see the opposite there. So for potassium, we have a higher concentration. We have 5 potassium on the inside of the cell, 2 on the outside. So we know that this is going to want to move outside of the cell. Potassium is going to want to move outside the cell when the neuron is at rest. Whereas sodium, we have a higher concentration on the outside and a lower concentration on the inside. So this sodium is going to want to move inside the cell. So now let's look at this. Again, with the potassium leak channel, we see that we have opposing forces. So concentration gradient is going out, electrical gradient going in for the electrochemical component for potassium. But for sodium, they're both going in the same direction. So yes, you can have situations where they're both going in the same direction, or one might be going in, one might be going out, or again, they're opposing at that point. But it's going to depend on having additional information to be able to answer questions about those details. Okay, folks, so this is another thing you want to know. The reason why we're bringing up this kind of slide is because, again, it shows you more leak channels specifically for sodium, just like you'll have another leak channel or an aquaporin for water when it comes to osmosis. And again, we have a good amount of these leak channels that are going to be within the membrane of neurons. So just keep that in mind. Now that we have all the information we can about what happens or how these ions, meaning sodium and potassium, are going to move passively using leak channel, let's talk about one of the most important proteins in the membrane when it comes to active transport. We'll see that in the next slide. So active transport, the difference between active transport and passive transport means that you need an input of energy in order for active transport to take place. Why? Because instead of going down the concentration gradient, going from a high concentration to a low concentration, guess what? This is going to do the opposite. It's going from a low concentration, so active transport is going from a low concentration to a high concentration. So it's not about simple diffusion anymore. So that means they're moving them against their electrochemical gradient. So if we're talking about concentration, sure, it's going to move against its electrochemical gradient, but that also moves things that normally go from positive to negative. Well, that can be now changed. the positives can then go back to something that's positive. And that's why it's very important to think of active transport, because there's more than one way to move ions, and active transport allows us to see the other way. So let's think about this. That means that potassium and it means that sodium has the ability to be moving towards the extracellular fluid, which we know is positive versus it being negative. But it doesn't happen specifically like that. So let's get into the details now. See our same setup. We have our cytosol, which is going to be negatively charged. We have our plasma membrane, and then we have our extracellular fluid, which is going to be positively charged. This is the outside of the cell. This is the inside of the cell. Same old, same old. What's the difference? Instead of seeing our leak channel proteins, we now see different membrane proteins. Again, these are going to be our primary active transport proteins, and these are going to be our sodium, potassium pump proteins. Now, some folks may say, well, why do we need to go against the concentration gradient? And the reason why is because we need to be able to, let me erase all this first. We need to be able to maintain the membrane, the negative membrane potential that we have here inside the cell. And how do we do that? We have to maintain the amount of potassium and sodium that are coming inside the cell. Now, why do we need to maintain that? Because remember, when we spoke about our passive transport here, the goal is that we're talking about neurons that are at rest. And we want to make sure that if we have all these signals and we're transmitting all these signals that we're receiving and transmitting for a neuron, when we're at rest, we want to make sure we can always go back to rest. How do we go back to rest? We go back to our overall membrane potential, or the negative membrane potential that we see inside the cell. And of course, we'll get into more details as we go along. So that means these pumps are going to pump out 3 sodium ions and pump back into the cell 2 potassium ions. And so again, when we go back here, we see that potassium's always leaking out, whereas sodium's always leaking into the cell. And these sodium potassium pumps help to change the way that they're going to be, the amount that we have of sodium potassium inside and outside the cell. So this sodium is going against its concentration gradient. It's going from something that is positively charged out of the cell to something that's also positively charged, that is against its electrical gradient. And also it's going from an area of low concentration to high concentration. Again, if we go back, we remember that sodium usually is going from high concentration to low concentration when it comes to the concentration gradient. Now we're going from our low concentration out to higher concentration. That's that little bit of a change to the actual transport as well. And that's the reason why active transport is important, because in order for these sodium potassium pumps to work, yes, you're going to need ATP energy. You're going to need that ATP energy. Now, in your book, they have this cool way, or I think in the study module thing, they have this cool way of showing you how to remember how many sodiums are going to be pushed out into the extracellular fluid and how many potassiums are coming in. So, for example, you have the neuron here, and then you have club intracellular, so inside the neuron, and then you have 2 bouncers. So one bouncer is going to see 3 sodiums come up to it and say, they're going to say, hey, can we come in? And they're going to say, nah, Na for sodium, right? And they're going to say, nah, you can't come in. Whereas when you have potassium, it says, hey, we're back in, let us in. And they're going to say, okay, right? And that's how you kind of remember that is potassium has the ability to come into the cell. Another thing you remember is pumpkin. I know some folks might also remember pumpkin. The pump allows potassium to come in. So whatever potassium does, the sodium is going to do the opposite. But for this one, it doesn't really tell you the numbers. So there's also other ways you can remember this, which is going to be just writing out Na plus and writing out K plus and looking at the characters. There's 1, 2, 3 characters here, 1, 2 characters here. 3 Na plus, 2 K plus or potassium. So 3 sodiums out, 2 potassiums in. That's just little ways you can remember it. Now let's go ahead and go to some worksheet examples. I'm only going to show you a couple of examples. And of course, just for the sake of the time of the videos, I'll probably just show you 1 example or 2 examples just to kind of get your brain primed. Now remember, these worksheets are given to you. And if you definitely need help with anything in the course, go to the home page and click on the course navigation video so you can just basically get your brain oriented of where everything's going to be. Let's go ahead and do number 1. So for number 1, it says, suppose the extracellular fluid has a chloride concentration, and it says chloride is Cl minus, of 120 millimolar. And then while the concentration of chloride inside the cytosol, or inside the cell, is 60 millimolar. So obviously the concentration on the outside is higher than the concentration inside. Before we even move on, let's go ahead and start to think this up in our brain. So with that, I'm going to be like, okay, well, first things I'm going to do is draw out a membrane. Now, we don't need it all fancy like we saw in the actual PowerPoint. We need to make sure we can just draw a simple line. And that is our line. Okay? And that's going to be our membrane here. And then, since we're talking about our chlorine and we're talking about concentration, we can go ahead and just add in some leak channel proteins for this. Here's a leak channel protein, okay, for our chlorine. And that means we're going to have chlorine being able to figure out the concentration amount and the electrochemical amount. Now, you already know this is looking like, hold up. Let me erase that. Okay, that's interesting. Going back to draw. Okay, boom, boom, boom. Now, let me just make this a little bit larger just so we can see. I'm kind of making it look like what we saw for the concentration gradient and the electrical gradient. Okay? Now, let's focus on the concentration gradient. What do we say? That we have 120 millimolar, and molar is for concentration, of chlorine ions on the outside, 60 millimolar of chlorine ions on the inside. So that means when it comes to our concentration, and we're talking about passive movement, we're going from an area of high concentration to low concentration. So for our concentration, we will have an arrow that goes inside the cell. Another way you can do this is for this line, you can write out and you can write in, just to make it easy. All right, let's move on. And it says also, suppose that the total net charge of the cytosol is more negative than the extracellular fluid. So it's telling us that inside the cell is more negative than the outside the cell, which therefore will be more positive. Now, because we're talking about chlorine, what does that mean? Chlorine is negatively charged. So will chlorine want to move towards the outside the cell, which is positively charged, or will it want to stay inside the cell? Well, because you have opposites attracting and doing opposite. If chlorine is negative, it's going to want to go to somewhere that's more positive, right? So my chlorine is going to move outside the cell when it comes to the electrochemical gradient. And so it says, given this information, which statement is correct regarding the movement of chlorine ions? It didn't say anything about an active transport or any kind of pump, sodium potassium pump. We're not even using sodium potassium, we're using chlorine. So that's another indicator that, again, is not about active transport or the sodium potassium pump, so keep that in mind. As we can see, when it comes to concentration, we're moving our chlorine into the cell. When it comes to electrochemical gradient, our chlorine is moving out of the cell. So for A, it says the electrical and concentration gradients both favor movement into the cell. That is false, based on our own diagram that we created from reading the question. So that's out. The concentration gradient favors a net movement out of the cell. The electrical gradient favors a movement into the cell. Okay, so that's kind of the opposite of what we see. The electrical gradient is going to be out. The concentration is going to be in. So that's opposite. So that's incorrect. Letter C. The electrical and concentration gradients both favor movement out of the cell. Again, that's incorrect. Concentration gradient is going into the cell. So automatically, D has to be the correct answer. So the concentration gradient favors a net movement into the cell. The electrical gradient favors movement out of the cell. All right, let's do another example. Let's do number 4 because it's kind of similar in this way. All right, let's go ahead and see. Terry was injected with a poison, so poor Terry, that blocks the sodium potassium pump. So if we're talking about the sodium potassium pump, we're thinking active transport, okay? And we're thinking about the protein, which is a sodium potassium pump that uses ATP to pump 3 Na plus out of the cell and 2 K plus of potassiums into the cell. With the sodium potassium pump blocked, what will happen to the concentration of potassium inside the cell? So for me, I'm going to write down as much as I can when it comes to this. First, let's do a membrane. What do we know about our membrane? Inside the membrane is going to be negatively charged. Outside the membrane is going to be positively charged. Then we need some leak channels because they're talking about concentration of potassium, so we definitely need some leak channels. So of course we have some leak channels just to keep it in for potassium, and then we're going to have our sodium potassium pump. Now we already talked about the pump here. We said that the sodium potassium pump is going to pump 2 K pluses into the cell and pump out 3 Na pluses. That part we know about the sodium potassium pump. When it comes to the potassium pump, though, you would have to know a little bit more information. Like, wait a minute, Potassium, what do we say? We said there's a higher concentration of potassium inside the cell. So that means potassium is going to want to move outside the cell when it comes to a leak channel. And that's just kind of bringing both these informations together. So now let's read the question. Terry was injected with the poison that blocks the sodium-potassium pump. With the sodium-potassium pump blocked, what will happen to the concentration of potassium inside the cell? Another way of saying this, if this doesn't work anymore, you're not pumping potassium back into the cell. So that means potassium is continuing to come out of the cell. So if you had a higher concentration of potassium, what's going to happen to that concentration of potassium? It's going to decrease because a lot of it's moving out of the cell through a leak channel. Let's continue. Letter A says the concentration of potassium will increase. That's false because potassium is moving out of the cell because the sodium-potassium pump doesn't work. It's blocked. The concentration of potassium will decrease. That is correct. Because again, it's it's potassium. I said it's potassium. Okay, I meant to say the concentration of potassium will decrease. That is true. I'm thinking of sodium-potassium pump. Tripping. Then we already know that because potassium is continually being pumped out, going from a high concentration to a low concentration. So that has to be correct. But let's look at number C. The concentration of potassium will be unaffected. That is not true because normally our cells are going to have a higher concentration of potassium inside the cell. So it's going to want to go through the leak channels and move outside the cell. All right, folks, I'm going to end here. And as we go in the future and we do more of these questions, I'm not going to do every single question, just to know that, because I know the videos can get long. All right, folks, see you in the next video.